We are taking the chaotic information of the entire internet, web pages, books, code, and funneling it into a single structured output stream. At its core, a language model performs a specific mathematical task. It assigns probabilities to text. To do this, the model breaks chunks of words into tokens. A token is the internal representation, the computational building block that the model uses to process information. During pre-training, the model sees a sequence of these previous tokens and attempts to predict the most likely next token in the series. This chart breaks down that calculation. The model predicts a probability distribution for the next word, like cat. We measure the loss, the negative log probability of the correct target, and use that signal to adjust the model's weights until it reaches the correct answer. By repeating this single-step prediction in a continuous loop, the model generates text one piece at a time. This process is known as autoregressive generation. Feeding trillions of tokens into this objective creates a system with immense fluency and broad world knowledge. But at this stage, it acts as a glorified autocomplete, lacking the structure needed for a useful conversation. The trajectory of modern AI began in 2017 with the publication of Attention is All You Need by Vaswani and a team at Google. This is the original 2017 transformer architecture. The multi-head attention blocks are key, allowing the model to look at every word simultaneously to process context in parallel. Finally, the data moves into feed-forward layers, where the primary mathematical transformations occur. Combining parallel self-attention with these dense layers eliminated the processing bottlenecks that restricted previous language models. By solving the problem of sequential processing, the transformer architecture provided the efficiency needed to apply exponentially more compute and data to the next token prediction problem. In 2018, the industry rapidly adopted this architecture, leading to the release of scaled-up variations, GPT-1, Elmo, and BERT. By 2019, OpenAI introduced GPT-2 and formally documented the scaling laws identified by Kaplan and colleagues. This first graph shows test loss against compute, visualizing a predictable relationship. As compute increases, the error rate drops along a power law. The second and third graphs verify this same mathematical rule applies when increasing dataset size and parameter count. This trend led to GPT-3 in 2020. At this massive scale, the model began to exhibit entirely new emergent capabilities. This chart details in-context learning. In the left column, the model performs tasks like translation using only a few prompt examples, without weight updates. This contrasts with traditional fine-tuning on the right, requiring thousands of examples and expensive updates for new tasks. By 2020, researchers had mathematically proven that making models bigger made them smarter, initiating a hardware race to build the largest possible prediction engines. In 2021, the push for unchecked scale met significant criticism. The Stochastic Parrots paper warned about the risks of prioritizing model size over data quality and safety. The fundamental flaw was the base objective. Predicting the most likely continuation of internet text often results in toxic, unhelpful, or repetitive outputs. A raw base model asked about the 2006 U.S. president might just list other politicians. A helpful conversational answer requires a completely different approach. The first solution was supervised fine-tuning, or SFT. This process trains the model on high-quality demonstrations to teach it a specific question-and-answer format. While SFT formatted the output like a chatbot, the field still lacked a way to optimize for subjective human values, such as helpfulness. Solving this required a shift in the training paradigm. To teach machines subjective values, researchers turned to reinforcement learning, the standard framework for training agents to maximize rewards through trial and error. This diagram shows a Markov decision process. It illustrates a loop where an agent takes an action in an environment and receives a state update and a reward signal. In the cart pole physics task, the goal is to balance a pole on a moving cart. The state is defined by position and velocity. Actions involve pushing left or right, and the reward, 1 point for every balanced step, is mathematically hard-coded. This highlights the alignment problem. Unlike balancing a pole, you cannot write a mathematical formula to define a helpful answer or a creative poem. The solution arrived in 2022 with the InstructGPT paper, reinforcement learning from human feedback, or RLHF. Instead of a hard-coded environment, researchers used a learned proxy, the reward predictor. Human annotators score pairs of AI responses, training this predictor to understand preferences. Finally, the RL algorithm optimizes the model's policy against this proxy, modifying entire responses rather than single tokens. RLHF bridged the gap between computational probability and human utility, transforming an unpredictable text generator into the fastest-growing consumer product in history. In 2023, the industry moved toward frontier scale with the release of systems like GPT-4. This marked an architectural shift to trillion-parameter mixture of experts models. As circled here, these models use specialized subnetworks to process different types of complex information. At this scale, RLHF faced a new bottleneck. RLHF relies on human raters, but humans can be misled by confident-sounding text and often struggle to accurately score advanced math or coding tasks. In 2024 and 2025, new models like o1 and Claude Code moved away from subjective human feedback. This introduced reinforcement learning with verifiable rewards, or RLVR. Instead of human preferences, models are optimized by checking objective logical outcomes, such as whether a mathematical proof is correct or if code successfully compiles. By replacing subjective feedback with verifiable logic, RLVR allowed models to transition from pleasing chatbots into reasoning engines capable of autonomous self-correction. This focus on reasoning established a different scaling law, changing how we measure AI performance. This O1 plot demonstrates performance scales by giving the model more time to process during inference. Notice the log scale x-axis. Allowing exponential compute time to search and backtrack dramatically increases accuracy on difficult problems. The modern AI stack consists of 3 milestones: pre-training for world knowledge, RLHF for human alignment, and RLVR for agentic logic. A unified data pipeline runs through all 3, from raw data at the bottom to verified logical outputs at the top. The last 8 years of AI follow an architectural journey, evolving from a system guessing the next word to an agent verifying its own logic.